anyone can build a website using Squarespace, the sponsor of this video. Around the 1900s, we thought physics was complete. Yep, we know everything. That is until we started analyzing the colors of the hot glowing things. I mean, we, who supposedly know everything, can surely explain what's going on over here, right? So we tried. We applied what we knew about guitar strings and air molecules to try and explain it. What could go wrong? What could go wrong? You might already know this. When classical physics tried to explain the black body radiation curve, it was a disaster. We called it the ultraviolet catastrophe. But I never understood what really happened. Why did it happen like that? I mean, surely you can understand the mathematical derivations. And by the way, if you want to do that, there are some beautiful videos out there and I have linked them over there. You can go through them. But for me, the intuition was missing for a long time. That is until, you probably know what I'm going to say, I read Feynman lectures and also went through all these amazing videos. So in this video, you and I are going to rediscover intuitively why classical physics leads ultimately to this ultraviolet catastrophe. And so if you're ready for this, let's begin. So Feynman, what's the whole issue with this hot glowing things? Well, Feynman reminds us that it's not just these metals that glow. Everything, including you, me, and donkeys, we all glow due to our temperature. We call this the thermal radiation. But what's important is that this glow contains all the colors of light, all the wavelengths of light, but they don't all get the same intensity. If you draw the intensity versus wavelength graph, as you can see over here, notice that some wavelengths, like say this particular infrared, gets very little intensity. But certain other wavelengths like this visible light gets a lot of intensity. And some other wavelengths again, like UV light, again gets very little intensity. And the big question was, why does the graph look like this? I mean, of course, the graph does change with temperature. I mean, at lower temperatures, the peak is in the infrared region. That's why most of us are glowing in infrared. And if you have very high temperatures, the peak can go even in the UV. And that's why very hot stars can actually give out a lot of ultraviolet and X-rays and stuff. But pretty much the shape stays the same. And of course, we've talked about the black body radiation graph in so much more detail in our previous video, but whatever I said in the last couple of minutes, if that made sense, then you don't have to go back and watch the video. I mean, let's not break the flow. But again, the big question was, why does the graph look like this? Why does a longer wavelength get very little amount of energy? And as the wavelength gets shorter and shorter, the energy increases, peaks, and then for further shorter wavelengths, the energy decreases again. Why this particular shape? Well, classical physics tried to explain it and tried to predict this, and when they did, that was a disaster. So Feynman, help me understand, why did the classical physics, why did classical physics break down? What was a disaster? Help me understand without any equations. And Feynman says, Mahesh, what happens when you pluck a guitar string? And I'm like, what? You get music. And Feynman asks, yes, but what causes that music? Sound waves. But what causes the sound waves? The waves on the string, Feynman. But what kind of waves? I'm like, oh my God. Standing waves. Yes, standing waves. Guitar strings, or strings of any musical instrument for that matter, create standing waves. These are different from traveling waves, which, well, they travel. But you know what? I find the word standing wave very weird, because wave is where you have energy moving from one point to another without the particles themselves moving. But standing wave, that means, is stationary motion. It's an oxymoron, kind of like bittersweet or acting naturally or internet privacy. But Feynman reminds us that it's called a standing wave because you get it when you have two traveling waves in the opposite direction and they interfere with each other. Again, check out this cool visual I did using ChatGPT and some video editing. I'm not trying to sell a course over here, but I'm super, super happy about how I was able to code that. So I'm proud of it. So yeah, it's pretty cool, right? But anyways, the same thing happens when you pluck a guitar string. There are traveling waves which hit the end, and since the ends of the string cannot vibrate, they reflect back and they interfere, causing standing waves. But is this the only way that you can set up a standing wave? No. The condition for the standing wave over here is that the ends of the string must be fixed. There are more than one way to do that. So another way to set up a standing wave looks like this. Look, again, the ends are fixed. And if you look carefully, you can see there are two lobes over here. And therefore, the wavelength over here is half of the wavelength in the first one. Can you see that? Okay, and therefore the frequency of this one must be twice the frequency of the previous one, and that's why the second one is oscillating faster. But at this point, I'm like, wait a second, I'm a little confused, and I always had this confusion. Why is it that the frequency must be double? Like, why should the frequency be higher if the wavelength is half? Why can't this oscillate with the same frequency as the previous one? And I don't want equations again. And Feynman says, well, again, think in terms of traveling waves. If you have a low frequency, then automatically, look, the wavelength becomes longer, and if you have a high frequency, look, automatically the wavelengths become shorter. So clearly, just from the animation, this beautiful animation that I coded myself, you can clearly see that the wavelength and the frequency have an inverse relationship. But anyways, coming back over here, why stop at half the wavelength? I can now have 1/3 the wavelength or thrice the frequency, and so on and so forth. There's no limit to it. I can keep on making the wavelength shorter and shorter and shorter, the frequency becoming higher and higher and higher. There's no limit to how much standing waves I can set up. And that's the kind of standing waves we get over here. But at this point, I'm like, okay, that's awesome and great and stuff, Feynman, but what does this have anything to do with black body radiation? And Feynman says, Mahesh, what do you think will happen if you were to heat up a hollow metallic cube with a hole? And I'm like, what? See, technically, this graph represents the thermal radiation of a perfect absorber, a perfect black body. You, me, and donkeys are not perfect. Now, even though we're not perfect, our thermal radiation pretty much looks like this. It's similar to this, even though it's not exact. But this metallic cube with a hole simulates pretty much a perfect black body. And I'm like, how? Well, the metallic cube is certainly not perfect absorber. I mean, it can reflect light. But if you were to shine light into that hole, then that light is pretty much gone. The chances of that light coming back out is negligible. So in that sense, that hole acts like a perfect absorber. Huh? And so if you were to heat up that metallic box and look at the radiation that comes out from the hole, just the hole, not the rest of the cube, but just the hole, then that thermal radiation will have a graph that's pretty much like this. And I'm like, that's pretty clever, Feynman. But again, what does this have anything to do with standing waves or guitar strings? Well, when you do heat up the metallic box, the walls of the container act like tiny oscillators, producing electromagnetic waves. And now, Mahesh, what happens when these electromagnetic waves travels forward, hit the wall, and reflect back? And I'm like, oh, just like with the guitar string, we get standing waves. And Feynman says, yes, exactly. We get electromagnetic standing waves. And just like with the guitar strings, you can now set up standing waves of shorter and shorter wavelengths or higher and higher frequencies. There is absolutely no limit to how short the wavelength you can go. So you can practically set up almost all the frequencies of light. And now the radiation that comes out will contain all these frequencies of light. And I'm like, that is awesome, because that now explains why at any temperature, a thermal radiation will contain all the frequencies of light. You, me, and donkeys are not just giving out infrared, we are giving out all the frequencies of light. Remember that. It's just that we are giving most of it in the infrared. But now that brings up the question, Feynman, how do we understand, or how do we figure out how much energy each of these wavelengths or each of these frequencies get? That's the $1 million question. That's what the black body radiation graph is, right? And it seems a little hard to do that because there are infinite wavelengths over here. So how do we calculate how much energy each one gets? And Feynman says, well, Mahesh, it does sound hard, or anything sounds impossible initially, but of course, if you can break it down and then build them up step by step, it gets easier. Kind of like what we do when we're building a website using Squarespace, the sponsor of this video. I thought website building was super hard, but let's break it down. Step 1, we need a domain, and you can get that directly in Squarespace. So I went there and searched for FloatHeadPhysics.com, obviously. It was available, and I purchased it, and boom, it went live within a few minutes. And I didn't know this, but you also get Whois Privacy for free, which is, important if you care about privacy and stuff like that. Step 2, now we have to build the website, but we don't need to start from scratch. We can just think about what kind of website we want to build. And then it gives us various templates to start with. We'll just pick something that we like, and immediately we get a skeleton of our website ready. Step 3, and here's where the fun begins. We can now hyper customize it to however we want. We can add our pages, photos, fonts, colors, move things around, and in a few hours, we have our website ready. And step 4, you don't just publish the website and you're done. No. You want to look at how your website is doing. And for that, you can head over to the analytics sections, which will give you all kinds of data, which you can use as a feedback to improve the website. And there you have it. Anyone can build a website now. And here's what's cooler. You can get started for free by heading to squarespace.com/FloatHeadPhysics. And yeah, of course, if you decide to make a purchase over there, you can save 10% by using the promo code FloatHeadPhysics at the checkout. Don't worry, the link is also in the description. Now, back to the video. So Feynman, I understand exactly why at any temperature, thermal radiation contains all the different wavelengths of light, because you can set up all the different wavelengths of light, standing waves inside that cube. That makes sense. But now the big question is, how do we compute how much energy each of these waves get? And for that, Feynman says, Mahesh, if you were to pour water randomly into these test tubes, which of them will end up with more water? And I'm like, what? How am I supposed to know? You're pouring it randomly. Any test tube will have more water. And Feynman says exactly. But what if we didn't have one set? We had not 5, but billions and billions of them. And we kept pouring water randomly in all of them. And don't worry, we have lots of water. Well, then some sets will have a lot of water, others will have less. In some sets, test tube 1 will have more water compared to the others, and in some other test tube 3 will have more water compared to the other. It'll be chaotic and all of that. But what if we looked at things on average? Meaning, if you were to take, let's say, all the water in test tube 1 and then added them up and divided by the total number of test tubes that we have, that would be the average water in test tube 1. And similarly, if we did that for test tube 2 and test tube 3, and now if we compared the average amount of water in these 3 test tubes, Mahesh, which of them would be more? And I'm like, I don't know. I have a feeling that it's all going to be equal. And Feynman says, exactly, it would be equal. It's kind of like tossing a coin. When you flip a coin, the chances of getting a heads and tail are the same because there's no preference. Now, if you flip the coin just like 10 to 15 times, you can't tell how many heads and how many tails you get. But if you did it like a trillion amount of times, you can be sure, because there's no preference, half of them would be heads and half of them would be tails. Statistics. The same thing's happening over here. Because there's no particular preference for any one of the test tubes, the chances of any of the test tube being filled to any level is pretty much the same. And therefore, when you do this like billions and trillions of times and you average it out, on average, the amount of water per test tube will be pretty much the same. And we can now build a theorem out of this. On average, water will always be equally divided among all the different test tubes. And we'll call this the equipartition theorem. And I'm like, wait a second, is there a theorem for water in test tubes? And Feynman says, no, silly, that's just an analogy. It's a powerful analogy though. But now consider your room full of air molecules. These molecules can move in 3 directions independently, along the X, along the Y, and along the Z. Wait a second, Feynman, can't molecules also move diagonally? Well, diagonal motion can be resolved as a combination of the motion along these 3 axes. But anyways, just like with the test tube, some molecules over here will move fast, some would move slow, and some would have more energy in the horizontal axis, others would have more energy in the vertical axis. But since there's no preference for any axis, on average, the energy has to be equally distributed among the 3 directions. That's what the equipartition theorem says. On average, energy, not water, is equally distributed among various degrees of freedom. Degree of freedom is a fancy way of describing the different ways in which energies can be stored. So for air molecules, the kinetic energy can be stored in these 3 different axes, and so there are 3 degrees of freedom. And so according to equipartition theorem, if the average energy for each degree of freedom is E naught, then the total energy should be 3 E naught. Makes sense, right? And by the way, if we had, say, diatomic molecules, like oxygen molecules, for example, then there would be more degrees of freedom. And at this point, I'm like, wait a second, Feynman, we're still in 3 dimensions. How can you have more than 3 degrees of freedom? Well, now, along with the motion along the 3 axes, they can also spin. That's additional ways of storing energy. In fact, they can spin in a couple of independent ways now. And total, therefore, they get 5 degrees of freedom. So in this particular case, if on average, the energy per degree of freedom is E naught, then the total average energy would be 5 E naught. Makes sense, right? Now, so far, this is all statistics, and we did this purely intuitively, right? But Boltzmann and Maxwell took this to the next level. They figured out that average energy per degree of freedom is proportional to the absolute temperature of the system. This was huge, because for a long time, we didn't really know what temperature meant. But now we do. The temperature is a direct measure of the average kinetic energy of these molecules. This was such a huge discovery back then because this meant that thermal energy was not a new form of energy at all. It's the same old kinetic energy, but at a much more microscopic level, which was like truly mind-blowing. It took thermodynamics to the whole new level. Temperature, which was a macroscopic quantity, got connected to the kinetic energy of these microscopic particles. And what was the connection? Boltzmann's constant. Now, of course, since we're not diving deep into the mathematics of it, we don't really have to worry too much about it. It's insane. That's why I just wanted to share that. It's incredible. But what matters for us, the key takeaway over here is that the equipartition theorem says that on average, energy would be equally divided among the different degrees of freedom. So if equipartition theorem works for gas molecules and water in test tubes, it should also work for our electromagnetic standing waves over here, because at the end of the day, it's a statistical theorem, right? So over here, look, each standing wave is an independent way of storing thermal energy, and therefore each particular wavelength represents a degree of freedom. And so Feynman says, Mahesh, Now apply what you learned about equipartition theorem over here and tell me what you get. And I'm like, okay, so according to equipartition theorem, on average, each of these wavelengths should get the same amount of energy. Let's say E naught. But wait a second. Remember that we can set up any number of shorter and shorter wavelengths. There's no limit. We can just set them up. So that means there are infinite degrees of freedom. And if each degree of freedom gets E naught, then the total energy will be infinity. Right? This is the problem, isn't it? And Feynman says, exactly, this is the crux of the problem. The problem is there is no limit to how short you can get your wavelengths over here. There is no limit to that at all. You can just keep on setting shorter and shorter wavelengths or higher and higher frequencies. And according to equipartition theorem, each of them on average should have the same amount of energy. So it's kind of like having infinite test tubes with you. It doesn't matter how much average water there is in each test tube. If there are infinite test tubes, the total amount of water would be infinity. And that's the problem with classical physics. It predicts that your black bodies at any temperature, because regardless of what the value of E naught is, the total energy output should be infinity. But wait a second. I understand that this is a disaster. Clearly, we're getting infinities everywhere. But shouldn't the graph be a horizontal line over here? Because each wavelength, each degree of freedom gets the same amount of energy, right? Why is it a curve? I don't see an ultraviolet catastrophe over here. I do see a catastrophe, but why is it an ultraviolet catastrophe? Well, Feynman says this is the last piece of the puzzle, and this is the one that took me a long time to understand. But the key idea, the last piece, is the standing string waves are one-dimensional, but the standing electromagnetic waves in that metallic cube, they are three-dimensional. And I'm like, okay, how does that change things? Well, in 1D, there's only one way to set up each wavelength. But turns out, in higher dimensions, there are more than one ways to set up each wavelength. And it's harder to visualize this in 3D, so let's look at it in 2D. Again, this is something that I coded myself. But anyways, okay. So if you look at the longest wavelength, which is analogous to what we see over here in 1D, then that looks like this. And again, there's only one way to set this up, okay? However, if you were to go for the next higher frequency, you can set it up this way, or you can set it up this way. These are the two ways in which you can have two lobes. Look at that. So since there are two independent ways to set up this particular standing waves, there are 2 degrees of freedom for this particular wavelength, not one. And for even shorter wavelengths, since you get more lobes, you can even set them up in even more ways, and therefore you get even more degrees of freedom over there. In short, as the frequency increases, unlike in 1D, where each of these wavelengths only have 1 degree of freedom because there's only one way to set it up, in higher dimensions, there are more and more ways to set them up. And as the frequency increases, the number of ways in which you can set up these standing waves also increases. And so the number of degrees of freedom increases. At this point, I'm like, Feynman, I kind of get this, but it's still hard to wrap my head around this. And Feynman says, okay, I'm going to take a slightly more mathematical approach, but we'll keep the math oversimplified so that we can just we can get the intuition out of it. In how many ways can a single variable take the values of, say, 1, 5, and 8? And I'm like, there's only one way to do that. X equals 1, X equals 5, and X equals 7. In each case, there's only one way to set that up. But what if you had a sum of 2 variables? Ooh, now there are multiple ways to set it up. For 1, you can set it up as 1, 0 or 0, 1. Both give you a sum of 1. But for 5, which is a higher number, there are more ways to set it up. You can make it 1, 5, 0, or you can make it 4, 1, and so on and so forth. And if you go even higher numbers, there are even more ways to set it up. So you can see by adding 2 variables, the number of ways in which you can set up increases. And if you had 3 variables, it would be even more. This is kind of analogous to what's going on. Again, the math is oversimplified over here. The actual math will involve squares and square roots and whatnot. But at the end of the day, this is what happens when you add more dimensions. This is why as the frequency value increases, there are more ways to set up those standing waves in 2 and 3 dimensions, and the number of degrees of freedom just keeps increasing. So if you go back to our standing waves in the cube, it's more appropriate to think that the low frequency infrared waves, they have less degrees of freedom, say about 10, just to give some number. The higher frequency visible light has more degrees of freedom, say 100. And the ultraviolet frequency, which is even higher, has even more degrees of freedom, say 1,000. And according to equipartition theorem, each degree of freedom is supposed to get E naught, So who ends up getting most of the energy? Still, the total energy is infinity, like we saw before, because there are infinite degrees of freedom. But within that, you can still see the higher frequency waves win. They are the ones that end up with most of the energy. And so what does the graph look like? It's not a horizontal line, but because there are more degrees of freedom per frequency at higher frequencies, the graph ends up becoming a curve. And this, therefore, according to classical physics, not only are you radiating infinite energy at any temperature, but most of that energy is coming out as high frequency, not really ultraviolet, but actually X-rays, because X-rays has the highest frequencies. I mean, you can have gamma rays, but gamma rays are quantum. Anyways, but you get the point. The point is classical physics predicts ultraviolet catastrophe. And by the way, this term ultraviolet catastrophe was coined much later. But anyways, if we zoom out, what is now the intuition behind why classical physics predicted ultraviolet catastrophe? Well, you have to put three things together. First, you can simulate a perfect black body as a hole in a metallic cube where you can set up lots and lots of standing waves. There's no limit to how short the wavelength can be, and therefore you have infinite degrees of freedom. Second, according to Equipartition theorem, each of these degrees of freedom should get on an average the same amount of energy, which automatically tells you that you'll have infinite total energy. But finally, the third piece is that the number of degrees of freedom actually increases with frequency because we're not in 1D, but we're in 3 dimensions. Putting it all together gives us that disastrous result, which predicts that everything should radiate infinite energy, mostly in high frequency ultraviolet or X-rays. So if this all made sense, and I really hope it did, the final question for us is, how does quantization solve all for this? What is the logic behind it? Well, that's coming up in the next video. But till then, if you missed my previous video, you can watch here. Here.